Okay, in this video we're going to do a air column question, and we're going to use that to use a frequency to determine the length of an air column. So you have a glass pop bottle outside on a nice warm sunny day, 20 degrees Celsius. You decide to blow across the top of the bottle to produce a sound. When you blow across the top of the bottle, you can observe a sound with a frequency of 400 Hertz. Determine the length of air column created by the pop bottle. Okay, so here you can imagine is our pop bottle, and we're going to send wind across the top of it, so some wave is going to form in here. And the simplest wave that's going to form is like this, right, where we're going to have a node down here and an antinode up here. So the length of the air column will be equal to a quarter of the wavelength. The formula here is that since it's closed on one end and open on the other, 2n minus 1 over 4 wavelengths is the general formula, and since we're not given any information in the question, we're going to assume it's the simplest one, n equals 1, which we go 2 is 1 minus 1 over 4, and that is just lambda over 4. So that's the standing wave pattern that we expect to see in this pop bottle, and that's going to produce a frequency of 400 Hertz. So what I want to do is I'm going to use the temperature to get the speed of sound, the speed to relate that frequency to a wavelength, and then once I have a wavelength I can go back and find the length of my air column. So first of all, the speed, given that the temperature is 20 degrees Celsius. The speed of sound is equal to 332 meters per second plus 0.6 times the temperature. So for 20 degrees, I get 344 meters per second. Now, if I have a frequency and I have a speed, I can use the universal wave equation to get the wavelength. 344 meters per second, frequency of 400 Hertz, and a wavelength. So if I divide both sides by 400 Hertz here, I get the wavelength, which works out to 0.86 meters, and that's going to be related to the length of the pop bottle. So here, for the simplest case, for the n equals 1, we'll do n equals 2, and we'll discuss the fact that that's a possibility as well, but we'll just do n equals 1 to start. Lambda over 4 is our relationship between the length of the object and the standing wave pattern. So 0.86 meters divided by 4 works out to be 0.215 meters. So that would mean that my pop bottle is 21.5 centimeters long, which is very possible. That isn't the only possible answer. Like I said, you use the n equals 1 because there's no information given in the question, and if there's no information given in the question, we can just, the n equals 1 standing wave is the most common or the most likely, but it could have been n equals 2. So let's just take a quick look at what the result would look like if it had been n equals 2. Remember, since we have a closed or a node on one end and an antinode on another, the general formula is 2n minus 1 over 4 lambda. So L is equal to 2n minus 1 divided by 4 over lambda. So if I put 2 into this equation, it works out to 3 over 4 lambda, which, for what it's worth, is the second possible standing wave pattern where we started a node, we go through one node that we don't use, and then we go up to the antinode, and that works out to 3/4 of a wavelength. So with that in hand, we can solve for the wavelength, which would be the length of the pop bottle, which would be 0.645 meters, or 64.5 centimeters. 64.5 centimeters is getting to be an awfully big pop bottle. So from a strictly physical standpoint, without using common sense, both of these results would be possible. But from a common sense perspective, we can imagine a pop bottle that is 21.5 centimeters tall fairly easily. 64.5 is a little ridiculous, so I'm going to assume that that's the correct answer.